Yeah, talk about that.
Since I'm booked 3 to 5, I may end up.
Alright,
I may
so
end up
give
doing
us
this.
a couple minutes to
Out of the nurses.
Monday and Tuesday, it's Monday, Tuesday, which is definitely conference time of the year.
I think we'll go ahead and get started and start through it. I don't know if you can, a couple more minutes.
Go ahead. I'll need the time.
Alright, so welcome everyone. I know we have a few new faces here, so I'll just give my brief introduction to the seminar series. This is the Tools and Technology Seminar Series for the Department of Computational Medicine, Bioinformatics. And it's basically just a venue to talk about and learn about tools, technologies. Sometimes they're newly developed, sometimes they're in development. They don't have to be a nice, formalized, polished product yet. Or just, you know, what is out there, tools and technologies that are out there that researchers have available to them and can use. So today I'm happy to introduce Brock Palen. He is, I believe, Assistant Director of Advanced Research Computing, the Technology Services Unit.
Do you want to introduce other folks about HPC today?
Yeah, I can do that. So I'm Brock Palen. I am the Assistant Director for Advanced Research Computing Technology Services. We work with a number of people in the room, of course, a number of the students and faculty we've worked with, but people who have a direct affiliation with ArcTS. We have Jeremy Hallam. He's one of the managers at ArcTS, but is specifically leading up our relationship with life sciences and things such as the medical center. Ken is, many of you know, also has a direct relationship and supports users on our system. He's what we call one of our liaisons. And so he's like in our joint support group and our support working group and a number of things like that that helps mold the services and what they are and gives feedback back and forth from the users. So this is a public presentation. This is going to be an overview we put together of all the different services that ArcTS has. Some of these are forward-facing comments. Some of them are currently available. I'll try to make that clear. If I don't, feel free to inject a question at any time and I'll address it. It is also a public presentation that we aim to keep updated as status of things change and new products come online. And there's a short URL here. Feel free. This is accessible to anybody. It's just a Google presentation and you can pick this up. This is our web address. You can follow me on Twitter if you want. But most importantly, remember this email address, hpc-support@umich.edu. That does go into our ticket system because this is also where users send questions and things like that. But it really is if you drop into there and say, like, we're trying to set up a project on Amazon Cloud and it's for doing large-scale sequencing runs or something like that, and we'd like to have some help, or what do you know, or the performance is low, can you help? Just drop stuff there if you're curious about literally anything having to do with research technologies in the IT space. So this is basically a quick overview. Any pictures of computers or data centers in here are of those here on campus. So this is actually a photo of the data center that Flux and Armis resides in. The lights are off, but as you can see, we buy LED stock. I mean, seriously, look at the number of LEDs we've got in there. So cool, so many LEDs. No, it's an unmanned facility. Nobody's in there unless someone's actively working on something because it's a very uncomfortable environment to be in. It can be as much as 90 degrees in this aisle right here, just a hot aisle, and it's very, very loud from all the fans and cooling. But what do we actually try to enable? We only have infrastructure to be able to support scientific work, so we're looking on, we provide systems, infrastructure, and consulting services. We try to deliver services at scale, so we try to leverage just buying power, administrative overhead, all those sorts of things we try to do and keep things as accessible but also as low cost as possible to the institution. But at the same time, as much as we have production research resources, we also try to do forward-looking things. So that's the respond to cutting-edge research needs. So we are very, very different than the enterprise organizations on campus. If anybody here is familiar with the Gartner Magic Quadrants of hype and stuff we're in the hype column a lot. while our peers in the enterprise group would be like, oh, that's in the hype column, we shouldn't go there. And we're like, why are you even listening to Gartner? I want to know what Facebook is doing. I want to know what Pinterest is doing, because their infrastructures and how they manage environments are more similar to what we actually do. So we do implement a lot of things in the hype column. We do partner with faculty, researchers, students, administrators, central IT, and unit experts. This last line is very important. So like Ken is an example of this. The University of Michigan has 101 top 10 graduate programs. It's really unique in the world in that respect. That also means that we cannot have domain level specific knowledge or relationships with all the different faculty and what they're doing on campus inside one single central group. It's just impossible. There's a classic problem in economics called the knowledge problem. How do you disseminate information and get it there quickly as possible? The way we do this is we scale where it makes sense, that is system administration and infrastructure, but we don't scale and we disperse where information is dispersed. And an example of that is the unit IT and the direct researcher engagement for what do you do and what are your needs? You know, talk to us and we get feedback. So if you feed information to Ken, he feeds it to us. If you want to go deeper in that and have a direct conversation with that, we're happy to do that too. But you know, really, he's your point contact for a lot of this stuff. Now, ArcTS is only one of 4 different units in Arc. So we're the only unit that has anything to do with IT in the traditional sense. If you've heard we're part of ITS, technically all the ArcTS employees are ITS employees, but we're funded by Office of Research. We're under faculty leadership, Dr. Eric McKeelson. So we're there organizational. We get like HR support and finance support, all that overhead stuff that we don't want to invest into. We want to invest into technology and science. So we reside here. We really focus on infrastructure. The other service group is CSCAR, Center for Statistics, Computing, and Analytics Research. If you're familiar with CSCAR, you might recognize that acronym is different than it was in the past. It's because we've expanded their scope. As they got reorganized under ARC, especially like things like the Data Science Initiative, we now have people here like we have Alexander Gayenko, who is a applications specialist. So he is able to parallelize codes, focus on performance tuning. And he's a PhD computational chemist. I mean, he developed a scientific code for a long time. Support here is both, there is a fee for using consultants here, but it's only after some modest amount. So they have workshops and open houses where you can come in with your code and they'll do a quick overview, or come in with your science problem. Like if you're doing a statistical study, they're very strong on statistics given their history, and they can tell you, it's like, oh, this will be faster for you, or this will give you more statistical power, or this is the appropriate way to do this. A lot of their customers are social scientists and things like that in the statistics space, where they're using statistical methods to really make sure that what they're doing is giving them, you know, useful results. So those are the 2 service groups. Brain, that's the easiest way to think about it. We bring the muscle, they do it smarter. There's a good example of this. We were working with a political scientist who had a 880 gigabyte data set. He was trying to use it in Stata, which is what their tool of choice was. Problem is 880 gigabytes with a tool like Stata or SAS or SPSS or MATLAB, it tries to read the whole thing in memory. Even though we have machines with a terabyte plus of memory in them, as soon as he tried to modify it, the thing ran out of memory and it fell over. So what we did is so his thing wasn't working at all. It was a 1.4 billion row CSV file. What he wanted to do was actually very simple. It was just big, so it was cumbersome. We put him on our Hadoop cluster, which is free, and I'll cover that later. And we put it in the Hive. 14 lines of code later, his query was now running in under 2 minutes. Great, right? Kirby, Dr. Shedden, who's a leader of this group over here, he's also has an appointment in statistics, took his need, wrote a Python code using advanced methods, and the thing runs on your desktop in like 10 minutes now. So, you know, we worked this thing up and got it going significantly faster than they could do before. So there's a nice synergy here. And there's a nice example here. So the other 2 over here are faculty-led institutes. We have the Computational Science Institute, MICDE. There's a graduate program here. There's affiliated faculty. There's a Data Science Institute, as you know. MIDAS, Michigan Institute for Data Science. So the Data Science Initiative, right? It was a set of investments into faculty positions, research, infrastructure, and consulting. Compared to most schools when they did this, they invested into one of those. They create a bunch of faculty positions, but they don't fund infrastructure or consulting. Or they put a bunch of infrastructure, but they don't have faculty lined up that do that sort of work. So Michigan actually did a very nice set of investments here. So the consultants reside here, socials. So you have specialists in social science, social media, big data, database design. Infrastructure resides here, Hadoop, software-defined databases, high-performance computing, in-memory analytics. And then you have graduate work, faculty organization around proposals, all that sort of thing here. Now, something I will stress is just because you're in one of these institutes doesn't mean you get preferential access to any of these resources. These are available to everybody on campus. So you don't have to be an affiliated faculty here to write a grant with us or to get help from us or use our resources. That's not required at all. Okay, so specific resources. This is what the bulk of the presentation is going to be on. And I start off with the one that you've probably heard of before. So this is what we're best known for, Flux, the high-performance computing cluster here at the University of Michigan. It is the largest cluster at the university. It's currently over 20,000 CPU cores. It has nodes at this time. So I mentioned earlier the political scientists, and we had nodes with up to a terabyte of RAM. Now we have a terabyte and a half. So if you want 1,500 gigabytes of main memory under a single operating system, my laptop has 16. A beefy desktop will have like 128. So we're 10x bigger. And that's really something you should keep in mind here. Everything we do 10x bigger than most people. So our performance will be 10x, our memory footprint will be 10x, our network bandwidth will be 10x, everything will be 10x. So we have up to 1.5 terabytes of shared memory, up to 54 cores. These are real cores, these are not hyper-threaded. So we actually have 54 core machines. If you have something that parallelizes or uses threads in a single machine, we have that. And we also have other technologies like NVIDIA GPUs. So you might have seen of general purpose processing on graphics processing units. We have those and support those with the full development toolchain debugging capability. We even have machines that have up to 8 GPUs in a single node, which is kind of ridiculous. It come in most people's minds, but to give you an idea, we actually, even though the GPUs here are like a generation old, we actually have the fastest benchmark on the Blender 3D rendering benchmark because we have machines that had 8 GPUs in them. So you can do some interesting things there. So that's like what the infrastructure looks like. Now, what are some key features? All these machines are connected by a 40 or 100 gig network. To give you an idea, the university backbone is only 100 gig. The last 136 machines we added to the cluster all have 100 gig. Our total network capacity is measured in terabits. This is a special network called InfiniBand. It's used for storage. We can technically run IP traffic over it, and I'll touch on that a little bit later, which is important for large data type flows. But it's mostly used for low latency. So if you have ever done parallel programming before, distributed memory parallel, there's a common method called MPI, Message Passing Interface. It's a standard that's ratified by a number of academic and commercial organizations. They have a forum where they define the API. It runs over that network. To give you an idea, our latency here is sub 2 microsecond. Good Ethernet, not doing anything funky with RDMA or iWarp and all these other things that are really not mature and don't. We've tested them, trust me, we've tested them. They're not quite ready for prime time, though we're excited for market competition in the future, is like 40 microsecond. And that's good. If you're like a gamer, right, you're normally happy with like 30 milliseconds. So look at how many orders of magnitude lower latency we are. And then super high bandwidth too, so like when you are sending data on the network, it's getting to the other computer as quickly as possible so that your CPU is not stalled out. Now that's handy for parallel computing. It's also handy for data intensive, even if you're not doing parallel, because our Scratch file system runs over that. So every machine gets about 1 gigabyte per second of I/O bandwidth capable over this network. So that's greater than 10 gig Ethernet speeds over that. It has a shared 1.5 petabyte Scratch file system. This is the fastest non-flash file system on campus in terms of actual delivered workload. It sustains several gigabytes a second, read-write speed continuously all day long, all the time, and it's completely shared. So when you get an allocation on the cluster, it comes with all the Scratch space you can eat, but it is a Scratch space, so we purge data off of it because people tend to write a lot of restart files, checkpoint, intermediate data, and then they leave it there, so we blow it away. It's very, very fast, and we can grow this pretty much as fast and as big as it needs to be. We do have HIPAA and PHI compliance and alignment. So we have a new cluster called Armis, you might have not heard of. Armis is identical to Flux in pretty much every respect. Scratch is a little bit different. Some of the access methods are a little bit different for tighter security control. So you lose a little bit of usability to a little bit stronger security, but now the HIPAA control group for the university I reside in the hospital has said you can put patient data. So it's also nice though, because going through this whole exercise, we had to document how you add and remove users, how do you do updates, how do you do physical access controls. We had a lot of that documented already, but now we have it all documented. And so if you have a data use agreement, like you want to get data, say, from an insurance provider, it's technically not HIPAA, but they have restrictions on prove to us that you will protect this because our entire business rides on this. Or location data, say you're getting like Fitbit tracker data or something like that, and they really don't want that stuff to get into the wrong hands because it ruins faith in their business. Armis sometimes fits the need for that because we have all this documentation of controls on how we control access and updates and security. 160 gigabit backbone connection. So the InfiniBand network can emulate an Ethernet network, and we have these boxes that make Ethernet to InfiniBand run over top of each other. Why is it 160 gig when the backbone's only 100? It's because of the way the technology works. It's 4 40 gig connections. And they're hooked up in a failover pair, so there's pairs of everything. What's neat about this is we let you bring your own storage. So on campus, a lot of groups that have large data needs have their own storage built out. Staging the data into Scratch takes time, especially if their data needs aren't that great. But they have a lot of it and they have their own storage. As long as you meet certain requirements, it's professionally managed, you use university UIDs to relatively easy to answer questions, we will directly mount your storage on the cluster over this gateway. And to give you an idea, SPH has 16 petabytes of human genetic data sitting down at the Mac on the other side of town. We mount their storage over this, and on a normal production run day, we will pull 20 gigabit a second, which is 20% of the entire backbone's capacity. The most we've ever done between this and Turbo coming in a cluster at once has been 40. So, and we've tested synthetically much higher than that, but that 40 was real world workload. So we can pull data into the system at ridiculously high speeds. To give you an idea, we have, broken's a bad word, demonstrated weaknesses in existing IT infrastructure given the speed at which we can ingest data. A network connection that's normally fine at a gigabit, we plug the whole thing with data flows. There's also a program where we give extra cycles for free to undergrad. So if you have an undergrad that has their own project, there's a very light vetting process just to make sure you're not picking up a UROP student to do your normal research. But if undergrad, so this is like student teams, work done here, an example of the Michigan Data Science team, pulled together all the public data sources on the lead in the water in Flint and generated some of the first high quality maps of where the water actually is and actually have a predictive way of we would expect your water to have this much lead. All that work was done here on the cluster on Flux under that program.
They'll talk about that this Friday.
Okay.
Jacob is talking in my seminar at 4 this Friday.
What was interesting about that is that work got a lot of traction. A number of companies wanted to sponsor what they were doing. We then helped them out because NVIDIA donated to them 2 professional grade graphics cards for doing computational on. So we bought the matching server and added it to our GPU service, and they now have 2 GPUs that are theirs on the cluster they can use whenever they want.
He's like Fermi.
Yeah, they're Fermi class. They were K40s. Pascal. I'll talk about Pascal later. We have a bunch of those coming too, with NVLink. The other neat thing about it is the cluster comes with a complete software environment. So we have an unlimited license of MATLAB along with most of the popular toolboxes, as well as 600 tokens of the MATLAB distributed computing server. All of those you get to use for free with your cluster subscription, so you don't have to pay extra. So it's funny because we have some faculty that I know use the cluster because it's cheaper to rent cores here and use the software than to buy the software and load it on their own machine.
Sure.
Yeah. But it's neat because we lump all of these together and the cost across everybody is like $1. So it's just provided that way. And it's neat. So we have, I mentioned MATLAB, we have Mathematica, we have common FEA, CIE tools, so like Abacus, Nastran, ANSYS. We have people who do, of course, the classic structures model, but they'll also do prosthetics for like dental implants and do an FEA model of that for structure to make sure it's not going to wear out after 30 years, stuff like that. ANSYS with all the CFD and CAE tools, SAS, Stata MP. This is something that is normally prohibitively expensive to an individual researcher, but we have Stata MP supported on up to 16 cores, and we have multiple copies of that. So that's the parallel version of Stata. And of course, we have R, which of course is open source, but we maintain a whole set of R libraries and parallel R and multiple versions of it. There's over 100 different packages that are on the cluster. And we install them and update them basically on faculty request. So just because you don't see something there doesn't mean we don't have the ability to install it, both commercial or free. Commercial, if we don't have it, is a little bit more of a hoop. And you can always bring your own software, but check with us first before you bother spending the money on it to make sure we haven't already did it. And then we have the full development environment, compilers, debuggers, math libraries, so your linear algebra packages, your random number generators, your Fourier transforms, your sparse solvers, all those sorts of things that are optimized for the processor architecture are all there. And I highly encourage you to use other people's code. One, it's probably been way more tested than what you can develop, and two, it's probably much faster. Especially the CPU manufacturers make their own math libraries. Intel's is called MKL, the math kernel library. I highly recommend you look into it, because normally it's a good order of magnitude faster than writing C or Fortran on the same hardware. Flux operating environment. So I'm not getting into too much about the different ways you actually pay for and consume for the resources. But this is an important one because a lot of times people think they can't do this. So the normal cluster is a subscription. You either pay for it as you use it or you pay for it monthly. Sometimes you have granting agencies that really want you to spend all the money for a 3-year project in one fiscal year. You have 1 year, you have to spend it all, but get your infrastructure you need to support your work. So we have this service called the Flux operating environment. Think of it as the Flux or Armis cluster minus the computer. So we provide data center, power, cooling, admin, the software, the shared storage, the login node, the queuing software, everything except for the actual processors and memory. Then what we do is we leverage our buying power. We work with you, get your requirements. We leverage our buying power because we spend a few $1 million a year on equipment. And we go to our vendors and we get you the lowest cost machine that meets your needs. And then we add it, and effectively it's yours for its life, which is between 4 and 5 years normally. It does end up looking exactly like the cluster, so you don't get as much flexibility in terms of configuration. That's one of the ways we scale the staffing. Not everything is completely customized, but you can get customized hardware. Say you need a little bit more memory per core, or you want a consumer grade GPU, which is terrible for FEA codes because it doesn't support double precision, but great for machine learning in terms of cost per performance. And we've actually done that. So we support Titan cards on here too. This is something new. This came out probably only like a month ago in terms of going live. ArcConnect is an easier way to use the cluster. There's no cost to using this. It's just a feature of the cluster now. You go to this web address, connect.arcts.umh.edu, and you get this web page. You log in through cosign. You have to use your M token, just like log into the cluster. The security profile is the same. But from here, you pick your allocation you want to run under. You pick VNC for remote desktop, which is what I'm showing over here. Jupyter notebooks, formerly IPython, so literate programming. RStudio, you pick your desktop size, number of processors, memory, software licenses, GPUs, all the usual things. You can't do advanced scheduling in here, but for the most common use case, this works great. And it does all the work of submitting the job to the batch system for you. So there's no Linux command line, batch script, learning every option. Literally fill in the boxes, hit start. When it starts, you get a terminal on a cluster node. Here it's 5788. All in your web browser, strong encryption, not virtualized. This is bare metal performance. You should see the same performance as you get when you run into batch queue. With the InfiniBand, with the software, with the shared storage. So this is a way that you can both visualize. So you can see here, I'm starting up MATLAB. The full GUI will start. You will get full GUI. You're not going to have the same performance as a local machine because there's no accelerated GL here. There is the ability to do that. The newest GPUs we just added do have the capability to do that. We've just not implemented it yet. That is something in the future to have full accelerated graphics. But otherwise, 3D does work. It's just don't expect it to be super snappy, responsive like your $1,000 graphics card in your desktop. But on the other hand, you're on a computer with 24 cores and 128 gigabytes of RAM. So that might be more to your liking than your desktop with 4 cores and 16 gig. The other nice thing is if you're teaching a course, you can have every undergrad come in, sit down, they log into this, they all get their own 2 cores and 8 gigs of RAM, or their own 16 cores and 64 gigs of RAM, or whatever it is they need, and not have to have that hurdle of learn the Linux command line before you can do anything. And then, of course, anybody, we've had people in the past where they'd hack into Jupyter server, into the cluster. It's now all completely automatic. You just click that radio button, say number of processors you want, and you get the Jupyter server running in your browser, but it's actually running on a cluster node, dedicated processors, dedicated memory. So unlike something like my desktop where you're virtualizing all these different desktops and piling 20 of them on a single piece of hardware, but you're trying to do something that requires performance, here you have that bare metal performance. The processors are dedicated to you, the memory are dedicated to you. So that's a neat feature about that. Then there's one final interesting feature, which is after this thing starts, you click on one of these tabs, there will be a unique link in there. You can give that link to a collaborator. There's a read-only and a read-write. And it creates a little session password. You share that with them in a secure way. So text them. Don't send it by email. You can send the link by email, but don't send the password by email. And you give them that password, and both of you, from across the world, if you're using the university VPN, can see and manipulate the same data simultaneously. So you could pull up a plot here, see something weird, call up somebody and say like, hey, I just sent you a link, click on it. Tell them the password over the phone. They can pull it up and be like, oh, that does look weird. And you can both work on it and control the same computer simultaneously. When you log out of the session, those unique passwords and stuff are all scrubbed, so it's only vulnerable for the lifetime of this session. But that is there for collaboration and interaction and hopefully higher productivity. So this is something we're really excited about. There's no cost to using this because it's just another way of using the cluster. So if you're using Flux today, you can use Connect. You don't even have to ask us, you just do it. So we have a lot of people interested in training sessions, classwork, as well as on-ramping, like junior PhD students who maybe have not touched Linux as much. Big data. So Hadoop. So we have a Hadoop platform today. It's what we call a technology preview. It's modest in size. It's only about 300 terabytes of raw disk, about 100 terabytes total usable disk in the normal world. It is still very fast at doing certain things. It's a great way of getting your feet wet. It's free. Come and use it. We have Spark on there. We have Hive, Pig, all those different tools. Also, if you go to our website, you can find links to training. I give a high-level introduction to the big data tools, Hive, MapReduce, Hadoop, Spark, so that you can kind of do your, get familiar with the environment. You can start messing with it. We do have in the works a plan for a significantly larger investment into Hadoop, something on the order of 3 petabytes of raw disk, 1 petabyte usable, 10 or 40 gig networking, something very much on par with the decent sized analytics clusters around the country. So if you're interested in using that, have at it. It's free. Just send an email to HPC support, ask for an account. We'll set you up on it. Also, you can sign up for that course and get you some information also. Yottabyte Research Cloud. So you might have heard about YBRC, as we call it, Yottabyte Research Cloud. This was a donation to the university from a company in Detroit of about $5.5 million in IT equipment. It's going to be built out over 3 years. The first build out is going on right now. But we do have some capability to provide these sets of resources. As soon as the rest of that's built out, which we expect by the end of the month, maybe it'll spill over into November. Is that right? Okay, it's his project. He owns the project, so if it fails, blame him. But we do have the ability to do this today. So the HPC cluster is a batch environment. Right? You submit a job, you get access to resources, even if you're going through something like ArcConnect. It's not good for setting up a database server where you have multiple people accessing data simultaneously, or transactional data, like where you're updating data on a regular basis from multiple entry points, or for data ingest. This would be something like creating something that remote sensors in the field collect data and are syncing to a single location for running analytics or running work on. That is what this is for. This is a persistent set of resources. So if you need a SQL database, so MariaDB or Postgres, this is just a representative list. What we will support will be faculty driven. This is all a Docker container based, so we can spin these up very, very fast, and we can scale them up and down based on needs. So we have SQL databases, Redis and Kafka. These are reliable data bus systems. It's like the way push notifications work on your phone. You have a data publisher and you have a data subscriber. This is the bus that data gets published to, and your analytics on the back is the subscriber. So this deals with all the reliability and things like that. So if I am getting push notifications about bad weather from the Weather Channel app, the Weather Channel is a publisher. They are publishing to, in my case, Apple's message bus system. My phone is a subscriber, so when it reconnects, like say I shut off my phone because I'm on an airplane, it reconnects, it picks up all the messages for it. What's neat about those is you can have multiple subscribers to multiple sets of data. So you can have data coming in and have maybe a real-time analytics pipeline, an archiving pipeline, and until all of them have picked up the data, Kafka and Redis hold on to that. So it's really kind of a neat thing when you can think about the whole life cycle of data generation, data ingest, data storage, and then analytics. So, we have a project here where we're working with a professor in engineering where they are working with a industrial controller manufacturer. So they have, when you have a big assembly line, you have all these different boxes controlling lathes and mills and lines, and they have certain data. How much power, what's the temperature, how many hours have I ran? And what they want to do is they want to do predictive failure analysis. These boxes effectively look like patient monitors, because there's also a project going on in the hospital using patient monitors for the exact same thing. So they're doing real-time predictive failure bleed out in the hospital. Here we're trying to do real-time predictive failure of industrial components. Because if you've got $1 billion factory with 300 people on that line and something breaks unexpectedly and the whole thing goes idle for 12 hours, that's a lot of money. On the other hand, if you're doing too many preventative maintenances, shutting the thing down on a schedule to check everything and replace bearings before they're actually worn out, well, that's also, so we want to reduce the amount of maintenance, but we also want to know when things are going to fail unexpectedly. So they're syncing all the data in real time through Kafka, and we're storing data, and we're running a Hadoop pipeline for doing analytics on it. Elasticsearch is a document database. So this is something you put text documents into, and you can search them, kind of like a search engine. We actually use this internally for all of our logs. We consume internally about a terabyte of logs a day, 500 gigabytes, and we can search them in real time. I mean, Ken can tell you how this works. He has a web page he goes to. If you've got a problem with a job, he can go there, search for your job ID, search for your username, and find all the information, all the logs related to your jobs. But those things really do come in real time. Syncing in from 1,200 different sources, it's really quite impressive, and you can scale it out. It uses the same indexing engine on the backside as the Google Book Scanning project does, Lucene. So this can scale to multiple petabytes of data, and you can search it in real time. So if you have text data and you want to be able to search it real fast, this is a really powerful engine for that. InfluxDB, Grafana, this is a time series database. We also use this internally. We pull about 30,000 metrics a minute off of our cluster. A time series database is literally, if you've ever heard of round robin database, this is basically what this is. But think of it as, I have a metric, say number of observations, right? I have a value, 26, and I have a timestamp. So in the last interval, I saw 26 observations. Okay, but here's a fun thing though. What if you could collect all of the data on a very fine resolution? InfluxDB is ridiculously fast at ingesting this. Like I said, we're doing 30,000 metrics a minute today on one hard drive. And this thing clusters and scales out. So you want to store 1 million data points a minute on different metrics. And then Grafana is a nice web front end. If you walk into our office, there's a Grafana dashboard on the wall that shows current file system performance, current cluster load. It's all updated in real time. We run that off of a Raspberry Pi. That's pretty easy. But we can create all of that for you because it's just a web page. But it's pulling data off of InfluxDB in real time. Apache Storm is a real-time analytics pipeline. MongoDB is an example of a NoSQL database. So if you're interested in that, Impala is a large-scale, scale-out, SQL-like data warehousing thing. So it's think of it gives you SQL, so you can write normal structured query language, but it doesn't give you transactions in the way Oracle would. But on the other hand, this will give you the ability to have a petabyte database and maintain performance. So it's a trade-off. HBase is in the same space. Cassandra is not SQL, but it's a similar kind of idea. It's a clusterable, large-scale database. You know, if you want to build a petabyte database, you can do it there. iRods is the integrated rule-oriented data system. This is a server you put in front of storage that has, we call it policy enforcement points in their language, but think of it as an event. New data comes in. Okay, kick off this pipeline. Pull out this metadata. Run it through this thing. Create a thumbnail of that large image that just came off the microscope and store it in 2 different locations. Or this is sensitive data. Log every access from every user ID to any piece of data ever. You can have these different pipelines. When an event happens, new data, touch data, update data, you can have different things happen. Yeah?
Your data ingest, you're saying you have all this real world, real time data coming in from sensors and whatever. This sounds a lot like what Amazon does with Kinesis.
Yep.
How comparable is it?
Kinesis is much more fleshed out than ours. Because we basically customize ours to whatever your use case is. The other thing is, this is all on site, and when I talk about secure enclaves later, something known as GloveBox, to use HIPAA data on a third-party provider, you need something called a BAA, a Business Associates Agreement, which is basically an agreement between 2 entities saying that in the event sensitive data is leaked, who makes the announcement, who pays the fines, who's accepting the risk. If we keep it all on campus, we don't have any of this issue, so we can iterate very fast. To give you an idea, we've been working on the BAA with Amazon for like 3 years now. Yeah. So if you have a different data use agreement that's sensitive but not HIPAA, okay, budget 3 years plus to get that. Yeah, so this is why we still do a lot of things on site. That said, a lot of these things I hope to, we will provide the service where we can help you get your data connected up to it and do all that piece and become more of a consulting group than having to worry about running gear. Because the goal is just keep enabling science. We don't actually care about the gear that much. We just have it because we have to. Like Flux, we measure is about 3 times faster than Amazon because it's not virtualized, it's bare metal, it's not hyper-threaded, and it's about 1/3 the cost. So okay, well there's that. So there's a factor of 6 difference. On the other hand, Amazon gives you a lot more flexibility for up and down. So pick your poison. That said, we do support, and we've actually recently published a paper with CLASP, used to be called AOSS, on doing climate simulations on AWS. So we do help with that sort of work. So like I said, this is just a representative list of thinking what's possible. We can host pretty much any server you need.
Are free?
To a point. So because it is a donation, we do have the ability for high-value projects in the institution where we could provide more resources. For the average faculty, we can provide a modest set of resources equivalent to a server for projects at no cost. Beyond that, there is a way to add on. And if it's something like, well, we really only need 1 server most of the time, but we have this symposium where we have a bunch of people working on the same set of data, can you scale it up for 1 week? Yeah, that's no problem.
People in the medical school trying to use their historical clinical data to webcam.
Can you answer that?
Like that right now,
Yeah.
not nothing with the webcam. HR is still sort of
Yeah. Yeah, so this is all pretty new. So a lot of people who have existing infrastructure are wait and see. It's people who have needs that hadn't been addressed that we're working with right now because they're like, we got to get this going. That said, this is a decent sized thing. As much as I said it's spread out over 3 years, in the first year we will have a petabyte of spinning disk, 300 terabytes of flash, well actually NVMe, it uses a new interface that's faster, and like 1,400 cores,
A little bit less. A little bit less.
a little over 1,000 cores, real cores. Every like 28 cores has a half a terabyte of RAM. And it's all on a 40 gig Ethernet network, so the data movement and everything is super fast. Also, a neat thing about the storage here is, especially when we get to the enclaves, is it's globally deduplicated. That means if you upload a reference data set, say you upload 1,000 genomes. Okay, the first copy, we store the 70 terabytes. You upload 1,000 genomes because you don't realize we already have a copy on there. It doesn't actually store the 70 again. It recognizes that all the blocks hash to the same value, and it just increments a counter saying like, hey, there's 2 copies. Here's your copy, here's your copy. If you make a modification to it, it stores just the difference. So if you, especially when we get to the sensitive enclaves, where we need to have people really isolated from each other, the data are still globally deduplicated. So if we have data sets like your enclave that can't see into this other enclave has the same reference data, we don't actually end up storing it twice. Drives the cost way down. So really, for the Yottabyte Research Cloud, and we're really grateful to Yottabyte and Paul Hodges and company for donating this to the institution and working with us on this. Just like AWS has the EC2 service, the S3 service, the RDS service, you will see Yottabyte Research Cloud, GloveBox, that's the enclave. Yottabyte Research Cloud, DSI infrastructure, that's the databases and persistent storage here. There will eventually be a research desktop also. Pretty much everything we make for the enclaves to support them will be available in a, I shouldn't say unsecure, but a more accessible, risk acceptance type way.
See, the thing with this that you got to remember is, let's say you wanted to do something and you could do it on Flux. We're not going to set you up on Yottabyte unless you've got an absolute, reason to be on Yottabyte. We're going to lean you toward Flux or Armis.
Yeah. Like if you just want to run compute jobs, and you're not like falling into the enclave use case where it needs to be really isolated from everybody else, just because we got it donated and we got some capacity, we're not just gonna give it to just anybody, because it's a large campus with a lot of faculty. So we will fill it up with the use cases that it is for. Turbo high-speed storage, this is also something that's available today. So in the past, the only storage offerings for research were MSIS or MyStorage. We have now created something called Turbo. It is a pay by the terabyte service. So if you need a terabyte of storage, you just fill in the form, say what machines you want exported to, and here you go. What's neat about Turbo is there's a couple of features. It's good for PHI, so it's good for patient data and restricted data again. It's very fast. It's 40 gigabit a second. To give you an idea, MyStorage's entire network connection was only 10. So we go 4 times faster than the entire network connection for all of MyStorage. That's another example where we found weaknesses in the infrastructure on campus, because we had a researcher fill it up doing genomics work and broke everybody else using MyStorage. So, like I said, in this case we weren't 10 times bigger, we're 4 times bigger. Sorry. And here's the neat thing though. They watched what we did here, and the new generation of MyStorage is actually based on this technology. So this is the other difference we do. We push technology forward faster because we don't do a 5 nines level of support. We're next business day. For cost and performance reasons and new technology, we take a little bit more risk in terms of availability. Now, I'm not saying we're completely gung-ho and we reboot things every day, but we don't have on-call staff and things like that. So that's a difference between like us and MyStorage. They have 24/7 support. And here's the neat thing though, because they're moving that same direction, they actually support our physical infrastructure. So we actually do have 24/7 support for the physical equipment. So if it drops off the network and completely dies, yeah, there's somebody who's going to fix it. It's your user question of, can I get more space, isn't going to get acted on until the next business day. So it's very fast. Also, another feature we did that we rolled out was mixed NFS and CIFS. So a lot of people think you can only use Turbo with the cluster. Not true at all. We have lots of people who use this without using Flux at all, because you can mount it on your own personal desktop, laptop. Supports roaming clients, so you can log in from a hotel room. But in the past, you used to have to pick between CIFS, which is the way you mount storage on Windows, or NFS, which is the way you do it on Mac or Linux. Actually, Mac you can kind of do either, but Mac was in the middle. But if you were Windows, you had to stick with one. If you were Linux, you had to stick with the other. We actually support multi-protocol. That is a single set of data on here. You can mount both onto cluster, which is Linux, and on your desktop, which is Windows. So this is a new feature to be able to have all your data working in one spot and support both Windows, Linux, and Mac clients accessing the same set of data. So this works today. It's available today if you want to use it. And it's a feature difference between us and my storage and MSIS storage. Again, it's good for, there's data publishing and sharing with Globus. I'll touch on Globus a little bit more later. So you can share data with others. Some schools subsidize the cost. I think most of you here are not affiliated with LSA. Basically, LSA is the main one right now. Okay. And you have multiple options here. You can get replicated or snapshots or unreplicated or without snapshots. They're basically options when you set it up. So like we have a group that has data they really don't want to lose. So they buy one volume that's replicated. Replicated costs twice as much because you have 2 copies of the data in 2 geographic locations. But then they have a set of data that they can download back from the data provider. So if it went away or they corrupted it, it wasn't a big deal. So they have a second volume that is unreplicated that's quite a bit larger, but then it cuts their cost for storing that data in half. Now that said, the cost here is about the same as my storage. It's like $115 per terabyte per year unreplicated. Replicated is like $230, twice that. We are working on 2 projects. One I will touch in here, but another one that's farther out that I don't touch on here, where we are aiming to provide significantly lower cost storage offerings to campus that don't match, they don't look as flexible, as nice as this, but especially for those of you who have very large data volumes, it makes sense to build it a different way. And we will probably have a service around that, but we're probably 3 years away from that. Network Connection Improvement Program. This is a set of funding we have to get data out of instruments. So what this is we will pay to get a fatter network connection into your office. So like if you have a CT scanner, an MRI scanner, a flow cytometry box, some sort of device generates a lot of data, and getting it out. So instead you've got a stack of USB drives that could die on you or something like that. We can basically get a larger network connection, and we pay for it, into your lab to be able to get that data off the instrument and out into the world to other researchers or to replicated storage or professionally managed storage, then stacking it up on USB drives in your office. So we work with pretty much all the network providers on campus, so Unit IT, ITS, MSIS, MCIT, or now HITS. So pretty much whoever owns your network, they do the build out, we pay for it. Grant consulting and collaboration. So this is basically us saying, if you're doing a grant that has infrastructure involved with it, engage us earlier during the grant cycle. You can use examples of some very large infrastructure grants. So like Conflux is a dedicated cluster we built. It was $3.5 million of equipment. This is the machine that has 40 P100 Pascals. So the fastest GPU that exists. There's 40 of them on this thing, each with NVLink. It's an IBM Power 8 system. We wrote that grant together with them because when you do a large piece of infrastructure like this, the funding provider wants to know, like, how are you going to secure it? Where are you going to put it? I mean, that thing kicks out a lot of heat and requires a lot of power. Who's going to manage it? All these questions, and we can answer all those questions. We even helped answering the policy questions because the faculty were like, well, 20% of this machine is supposed to be available for non-PIs. It's like, well, we looked at the national providers we work with and their policies for dishing out cycles to different people and their refund process and all of that. And we're like, how about we adopt the policies of the NSF provider, the national provider? And they're like, okay. And so we had a well understood set of things, and because we have all those relationships, we did that. So yes, engage us earlier on. Talk to Ken, talk to Jeremy, talk to me, and we can contribute language. We can contribute letters of support. CSCAR with the consultants, we sometimes split staff. So say you need a software developer, but you can really only justify half their salary for say like 2 years or 3 years. We're like, okay, we'll pick up the rest of it and find another faculty to use the rest of their time. And when we do that, they actually sit in your office for the time they're working for you. I mean, they work for you. But we provide bridge funding to keep them on campus so we can attract better talent, because they're not really, they're being paid off of soft money, but at the same time, they have a backstop, so they don't have to go look for their next job right away. We do work with external providers. I already mentioned AWS. GloveBox is a file transfer service we have. I don't know if any of you have used this. This allows for data sharing and other things. And a lot of our testing is 2.5 to 3.5 times faster than SCP. It also deals with machines rebooting, network connections coming and going away. It deals with firewalls automatically. It's very nice. It uses the same protocol the Large Hadron Collider uses for moving around a couple of petabytes of data a day. Grid FTP. It's very nice, and it's all in your web browser, so it's very easy to use and understandable. And if you're doing a large transfer, it just emails you when it's done. And then we also support other providers and ourselves. So like the DOE Leadership Computing, this is the largest supercomputers in the country and the world. We will support you on things like Titan and Mira and Aurora. You know, those machines, we will help you with that. We tend to have accounts on all these machines. Exceed is the one that's more accessible. I'm the Exceed Campus Champion. What that means is there's actually a formal arrangement between NSF and the university for my time to build bridges between our faculty and the NSF built resources. So Exceed's a place where you can get CPU time, storage, consulting for free. You just have to submit a proposal to them. And to give you an idea, it's way easier to request time here than the equivalent amount of dollars to build or buy. So highly recommend that if you need a lot of compute, go here. They also have some unique machines. There's a machine here with, I think, 800 terabytes of flash attached to it. There's a machine here with 12 terabytes of shared memory. There's some interesting things going on here. So these are things that are forward-looking. So GloveBox, already mentioned the Yottabyte Research Cloud. GloveBox uses that software-defined infrastructure to create a private data center, or virtual data center, or VDC. Now, what is this? Picture if we had the ability to give you a virtualized desktop, a virtualized file server, a virtualized HPC, a virtualized database. We can give you all these different things. We have Docker containers or profiles for every one of these things, and we can spin them all up. But because of data use agreements, this thing needs to be really locked down. So here's what we do. We take all of those things and we put them on a private virtual network inside the VM environment. So if you're familiar with AWS, which I get the impression at least one of you in here is, this is like a virtual private cluster of VPC. Then we have one of these very tightly controlled Bastion hosts. It's normally a Windows desktop, but it can also be a Linux desktop, that you can connect to with remote desktop. It's accessible from the outside world, but it's the only thing that can see into this private enclave behind it. By locking everything down at the border, we don't have to actually tightly lock down everything inside that border. So like today, if you were hardening infrastructure on campus, you'd have to take your file service and make it, pass FSMA requirements. You'd have to take your, desktop and your physical location. It's like here, we have it all done. So if you want to do FSMA, we have all the designs. We go to the auditor. We say, like, we're reusing this exact same design we used for the last project. And you're like, okay. And we just spin it up. But the nice thing is, because it's all software defined, private cloud, you need another virtual desktop because you have a new student? Okay, it's already been signed off. We can clone it instantly. You need more storage attached to your server? Okay, we hook up more storage to it. It's very flexible. Yeah?
What about a user defining their own Dockers? Or are they all pre-selected?
Okay, so for the restricted enclaves, it's pretty much pre-selected, but that's obviously with effort flexible. Actually, on the HPC cluster, our batch system right now can actually launch Docker containers as a job. We've not tested it. It needs to be done. We're looking stronger at something called Singularity. Singularity is a container project that's focused for scientific computing, so it's not designed to run like a persistent service, like a web server, but it's really kind of neat. So like there's a MRI analysis software that has not been updated since 2012 or something like that. It does not currently run on Red Hat 7. It just bombs out. There's no compatibility libraries. what we were actually able to do is we were able to create a Singularity image container, which you can import Docker containers into Singularity, which basically has all the Red Hat 4 runtime, which is what this thing was designed on. And the user can actually submit that as in their job. So they have their batch script and they run Singularity image name executable that's inside the image. We map in our Scratch directory, we map in home, it squashes root so you can't see anyone else's data. So it's really kind of neat. So containers will be a regular thing going forward.
I would say that for the non-restricted, like Yottabyte response stuff, you're entertaining other people not registries.
Oh yeah, most definitely for the unrestricted one. But today, with a little bit of effort, we just have to, the project's not quite rolled out general yet. You'll be able to take Singularity containers and run those on the HPC cluster all you want. Singularity comes from the guy who started CentOS project, and it supports MPI and all that stuff too. So it's really quite neat for bringing your own environment and then making that reproducible. And we're very interested in containers for reproducible science. You can basically freeze that run in time with everything inside the container. This is another thing. So this is a different storage offering than what I mentioned earlier. So Turbo is fast, reliable, not cheap, right? It's very fast, very reliable, but it's not the cheapest thing there is. This, on the other hand, is extremely cheap, reliable, but not fast.
It's like Amazon's Glacier.
This would be similar to Amazon's Glacier. It's an HSM system. It's a tape robot. It's got cache disk in front of it. You put data into it. When that cache gets full, it writes it off to tape. The business model here is as important as the technical features. That is, this is designed to take one-time funding to store data for 10 years. So the way this is designed is, if I get everything I'm asking for, this is a little bit forward-facing, the price per terabyte here is going to range between $4 and like $35 per terabyte per year. Now, I'm going for the $4. Now, what is that? It is, you're at the end of your project, you want to archive a bunch of data. You want to keep it around so you can retrieve it to do future work with, but right now, you don't have funding to support it, but you've got $230. It's a magic number. $230 buys you 2 tapes, one that goes in each replica site. That gives you 6 terabytes of uncompressed storage for 10 years. One-time cost, $230. That's what we expect to be able to do. We're working on this with the library. Now, this is different than Deep Blue data. Deep Blue data is when you publish something and you freeze the data and you give it to the world so it's accessible and everything. This is when you still want to control it. Now, why are we working with the library on this? They're interested for Deep Blue data for large data sets, possibly back-ending Deep Blue data with this service for the larger data sets so they can cost-effectively store data for a long period of time. Now, I say it's not performant. It's not performant in the sense that you can't compute directly against it. So Turbo is fast enough, you mount it, and you can run right on it. This, on the other hand, you can't do that. But a tape drive can hit 300 megabytes per second plus. So if you've got large genomes, a big zip file of a ton of data, and it's large, after it's in the drive, it will spin off of there actually very, very fast. So that's what this is. This serves that need of storing data for the long term. So this is not meant to take business away from Turbo. It serves a different use case. What this is USB drives you stack on the shelf in the corner of your office, which are susceptible to bit rot, susceptible to damage, susceptible to theft, susceptible to not getting funded again if it's sensitive data and they find out you're leaving it in the corner in an unlocked office. So this is meant to address all of those needs. We do hope also that we'll be able to connect Globus or some sort of data publication thing to this also. So if you have a large data set on here and you want to get a copy of it to somebody at Berkeley, you type in their email address and they get a magic link and it can just download to them.
Now, with Glacier, I know that the cost of putting data on to Glacier is relatively cheap.
Yeah, it's nothing.
But getting it off of it is a whole different ball of wax.
Yeah.
Not the same.
So data egress out of Amazon is about 10 cents per gigabyte, right? Which technically right now the institution has a waiver for research cases. MOOCs and enterprise stuff, no, but you technically have a data egress waiver for research. Glacier has a number of problems. One, it's 3 times as expensive as this, based on my business model. 2, it's at a cloud provider, so BAA, restricted data problems again. I did not want to actually build this. I wanted to use Glacier. I tried to munch the numbers every way I could. Glacier also charges you a surcharge if you delete the data before 90 days or retrieve the data before 90 days. On the other hand, I see the archive use case being one that the most recently placed data is probably the most likely data to be accessed again. So the exact opposite of the Glacier use case. So in this case, because we control it and we control the cache disk in front, we can actually, there's no cost to that. Literally here, you might pay for with time, but Glacier already has horror stories of wait 4 hours to get your data, right? So it's really the exact same system, but we're going to put cache disk in front and we're going to manage it differently. But long term, I really hope that we don't have to take up floor space with this thing. It is neat though. Technically, we can expand this out to, was it 3.6 exabytes? It'll cost you a pretty penny, but we can technically do it. And actually, even at the, so this is based on a design of 5.5 petabytes replicated, so 11 petabytes of raw space. We did a model where we did it on 10.5 petabytes, 20 petabytes raw space. The cost to the institution still goes down. So this thing actually still scales out at a very high volume. Also, tapes are designed for a shelf life of 25 to 35 years. As opposed to disk, you're lucky if you can read your data back after 7 years. So this really is a more secure way of not losing your data. But also, it's going to be encrypted through and through, so the tapes, we might even have a service with the library where you can pick a subset of files, encrypt it with a different encryption key, write it to a tape, and eject it, and you can pick it up at the circulation counter just like you're picking up a book from the interlibrary loan. And then, because sometimes a station wagon full of tape is faster than the internet. Because if you can put 100 terabytes in a suitcase and get on a plane, it's a faster way to move a lot of data.
I almost have to ask why you're so reticent about giving up some floor space to this, because given the nature of science, we need to keep a lot of data for a very long period of time that it's just not cost effective to store it on Amazon.
Right, right. So it's actually not floor space. It's mostly just the effort in maintaining and feeding the robot itself. That takes labor. When you give it to a third party, they deal with it. So we can focus on the higher level service of turning it into something that faculty and graduate students can consume. That's the important part. We don't care where the bits land. We just care that it meets all regulatory needs that the faculty are getting funding sources and data sets from, that it meets technical requirements, and that it's actually accessible and usable, and then cost effective. So yeah, I mean, if we shipped it off-site, we really don't care. And that's why, like, we support AWS. We support the Exceed clusters. The old mantra was we care about computing, not computers. With storage, obviously, you change the words around a little bit, but same idea. So if we can free up labor to directly work with scientists, I think that's better for everybody. But it has to be cost effective. Right now, the cheapest way is to throw labor and buy gear at the large scale. That if you need to run a web server, it's way cheaper to run on Amazon for 25 bucks a month. So that is everything. This is our contact information again. HPC support is the magic email address. That's the ArcTS Twitter. Mostly tells you like when the cluster is getting updates and stuff like that. And you can email me there. So that's everything I had. So only a little bit over on time. So any questions on anything? Yeah.
You mentioned something about getting more Pascal GPUs. So what was that? Which project was that? When is it coming? And, you know,
So they're basically on their way right now. So the Conflux cluster, which was an NSF MRI proposal that was co-written between ARC staff and MICDE faculty, is a $3.5 million data-driven computational physics cluster. It's got a bunch of IBM Power 8s and a bunch of IBM Minsky servers with 4 Pascals with NVLink all connected up together. So it's really the flagship way, the way NVIDIA envisioned how these GPUs will work. So they've got the NVLink directly into the processor main memory as opposed to going through PCI Express. If you don't know, Intel will not implement NVLink because they have their Knights Landing. They don't want people to use GPUs. We have mics also, Xeon Phis, because we will support what the faculty find useful. With that project, we got early access, and so basically they're on their way right now.
But that's not for everyone.
So 20% of the cluster is supposed to be made available to non-PI users. That probably won't happen until next year, but that said, if you have a small project, ask. The faculty working on this are very amenable to other people utilizing their resource. The Pascals are not on there today. There's a rack marked off, and they're on their way. We have 2 K80s in there right now instead to kind of do development work.
Another question would be, so for these kind of machines, especially for machine learning on GPUs, often the bottleneck is not the GPU, and then, I mean, the first bottleneck is GPU, but then if you have a modern GPU that gets better, then you have bottleneck a CPU, but then if you have enough CPUs on the same machine that gets better, bottleneck becomes storage, and that's why a lot of these architectures are built in a way so you have, for example, hard drive for like as a temporary storage, then you have one SSD for OS, and then you have super fast SSD to actually serve data to GPU. You guys doing something like that in your?
So Conflux, because it's a machine learning platform, every node also has like an 800 gig flash or NVMe drive local in the node. And you mentioned an OS drive. We don't even have an OS drive on those machines. They boot from the network.
Yeah.
So we have an 800 gig thing sitting there that is flashed directly inside the node. And then Conflux sits on a 100 gig InfiniBand network connected to a petabyte of IBM GPFS file system. That they just tuned it the other day. What did they get, 7 gigabytes a second out of it or something like that? Yeah, so we have a 7 gigabyte per second file system. That's the slowest thing you have, because obviously that's shared across the entire cluster. Also, I mean, if you want Pascals, I mean, we can just add them to the cluster. Actually, Dr. McKeelson and myself, NVIDIA created this thing called the DGX1. It's their machine learning appliance. We were looking at just buying one of those for campus. Eric did not realize how expensive they actually were.
Pascal itself?
It's $113,000, but you're required to buy at least 1 year of their maintenance, which is like another 30. So you got to have 150 grand before you even talk about one of these things.
Yeah, because we are getting a couple of Pascals, but then probably going to build the machine ourselves. So I'm just looking in there, like, is it worth it, or is like maybe it's possible to do something with you guys? Or?
Yeah, so there's multiple ways to slice it. If you're not exactly sure that this is the direction you want to go and you don't want to invest into it yet, get a GPU from us for $100 for a month and just test it first. Now, the fastest thing we have is a K40, right? So it's not going to be Pascal class, but it'll still give you an idea of how does that compare to a CPU. Because I can tell you.
Oh, we did that before.
Oh, you did that already?
We have Pascal Maxwell, the previous generation one.
Okay. Okay. So then what you can do is if you want specifically a Pascal architecture or a Maxwell architecture, because those are better for the machine learning, you get the half precision and single precision and the higher memory bandwidth. We have a faculty that has like 64 of these on the cluster right now. We can actually just, under FOE, add on to the system machines with very specific cards. Now, okay, FOE sounds great because you can get exactly the thing you want. Here's the deal, though, compared to just renting stuff from us, we're constantly refreshing things. Like we just added K40s, but we added more K40s. We also have a bunch of K20Xs and K40s. If you buy a machine and you run it for 5 years, when it's 4 and 5 years old, the technology on it's old. On the other hand, if you're renting it from us, we've already refreshed or added at least where you can test the new technology. So it's a little bit of a trade-off. So the brand new machine may be the fastest thing, but it's going to end up being the slowest thing. On the other hand, if you're getting from us, you're getting a mix of something that's a couple years old, something that's brand new, and we kind of always have this nice average that's across its whole life.
All the libraries and then CUDAs that get released like every year.
Yeah, we have all of that too. So you log into our environment, we have something called modules. You module load CUDA /8.0, you get CUDA 8 because that just came out.
Is the default automatically set to the newest, or is it?
No, we don't adjust defaults rapidly because we're worried about reproducibility and changing stuff from underneath people. So we normally only change defaults for high-profile things at a defined boundary, normally one of our OS updates, because now we're also updating glibc and everything else on the cluster. So we tend to move everything forward then. That said, we will install whenever. we just added a bunch of Titan Pascals to the cluster for this faculty for machine learning. Those required CUDA 8, which was funny because we literally installed those like 4 days ago. So it's the CUDA 8 release candidate. And then they released the stable one yesterday. It's like, we missed it by like 48 hours to have the stable one. But the point is, since that hardware required it, they did have a newer version of the driver, but the toolkit was available wherever. So yeah, we tend to have many versions and permutations of versions of software on the system. Obviously, driver level stuff's a little bit different because it has to match the hardware, and you can't change that as rapidly. But yeah.
Oh, it's also the same for example, if you want to run like a Docker or something, then to mirror that on the hardware, drivers versions have to match in your Docker and in the machine. So
yeah, if you want to use Docker, especially with hardware pass-through. Yeah, it's getting harder than it was in the past because people want more than just CPUs, and everything is a little bit different. We even have faculty talking to us about FPGAs. So around machine learning, so you probably have seen the Google Tensor processor. The processor that's optimized for machine learning because it's like a fuzzy processor. It doesn't give you an exact answer, but you got way more silicon back to make it more cores. What if we could do that in FPGA so you could have other flexibility but also implement that sort of thing in hardware on the system and have it attached to a processor? So it's like, this was an interesting idea, and there might be a proposal going out the door on that sort of work.
Thank you, Brock. I think we'll take any other questions offline.
Okay. I've got a stack of cards here if anybody wants comments.